I'm going to turn this over to my friend and colleague, Danny.
Better? Yeah. Green light gives it all, yeah? Welcome to the last session of Pivot. Yeah, we're going to be talking about the startup competition. Yeah, and probably the minute that I started speaking, you realize three things. Yeah, first that I'm not American, I'm Spanish. Yeah, which means that I have traveled a long distance to come here today, and my jet lag is here. So if I ever mumble or miss something, blame it on the jet lag. Yeah. The second thing that you probably notice is that I'm wearing running shoes. First of all, because I look taller. Yeah, but mostly because I want to symbolize what the startups and what geothermal has to do, which is to run. Yeah, we have to run as an industry to catch up with other renewable resources. Oil and gas has to catch up and really normalize the situation of using oil and gas technologies and people into geothermal. And the startups that we're going to be seeing today are the ones that are running faster. Yeah, they're running to try to develop their ideas and deploy them in the field. Yeah, so I'm very excited to be the host of this competition. And I'm sure that they will be very excited about this competition, what they hear, what the prize is. Because in this third edition of the startup competition, we're really trying to put the stakes as high as possible. And the winner will not just get your applause, your recognition, they will also get a ticket to COP28 to come with us into the main stage to make a nice announcement about geothermal in the Middle East. Yeah. So bear in mind that we're not just, I mean, that's quite a nice prize, I would say. Yeah. And in order to be as humble and as neutral as possible, because in InnerSpace we know we have to be as neutral as possible and stay in the middle of everything. Yeah. We didn't want to give the advantage of the two people that are here. So we put both Simon and Cindy, that you've seen them around, they're going to be pitching. We hid them in a secret location inside of this building. So they're not going to be able to hypnotize our judges and have some sort of advantage out of that. Yeah. So now it's that time maybe to, and again, since this is such a nice competition with such a nice prize, we decided that we wanted to have as solid as possible, a very nice lineup of judges. They're here. We thank you. I would never thank you enough for doing this. Yeah. I'm going to very quickly introduce each one of them. Yes. So we have Rami Yassin, SVP of Drilling and Evaluation Division in Halliburton. We have Michael Weber, that was just recently introduced. You should remember who he is, but he's a CTO of Energy Impact Partners. He's also a professor in UT Austin. We have Matt Foser, the SVP of Growth Projects in Weatherford. That's where the geothermal line is sitting right now. And we also have Salvador Ayala. He's the head of the oil and gas portfolio strategy. Yeah. So we're going to be seeing now the pitches of these 5 companies, 5 startups. Yeah. And we're reviewing today, and we noticed that they're coming from 5 countries, which is great, some diversity. They're coming from 2 continents, Europe and America. So we're actually missing a little bit more diversity. So I don't know to which camera I have to look, but those people in India, in any country in Asia, or in Colombia, South America, or in Africa, Nigeria, Kenya, we want to hear your ideas, and we challenge you to come next year with brilliant ideas and participate in this competition. All right? Enough of me. We're going to be moving now into the videos. We're going to have 5 pitches, and after each one of them, we're going to allow our judges to judge via questions, some softballs, some hardballs, but we'll have that engagement between the judges and each one of the participants. So let me maybe cue in the first video. Yeah.
Hello, Houston, and hello, world. Hi. Thank you, Team Project InnerSpace, for organizing this great global event. It's a great honor to be in this contest and present the startup Canopus. Canopus has been named after a very bright star in the sky, which is a so-called supergiant, and ambitious we are. Diederik and I, on the top left photo, started Canopus in 2019, and currently we are with about 5 people. On top of that, we have more than 10 consortium partners with whom we execute a multi-million subsidy project on our directional steel shot drilling technology. But what is directional steel shot drilling, or DSSD in short? The technology has 4 components. First, there are the steel shot particles themselves. They are smaller than 1 millimeter. These are injected into the pressurized drilling mud by the injection unit, and the steel shot is then pumped through the drill string to the bit, where the steel shot erosion joins the PDC bit cutting action. But just before reaching the bit, the steel shot particles flow through the steering sub, which converts the constant supply of steel shot into concentration pulses. This slide provides a bit more detail on the steering sub. The graph insert at the top, the middle top, shows steel shot concentration pulses created by a dual tube section. The steering action comes from an increased steel shot concentration, increasing the erosion of the jets at the right moment. And the right moment is when they are aimed in the steering direction. That is, the jets are aimed in that direction. On the right-hand side, an S-shaped borehole in hard limestone was drilled with this method. The steering action is very strong, as you can see. The DSSD is capable of making a 90-degree turn within 10 meters. Of course, that steering action can be reduced to match the stiffness of the drilling assembly and possibly the completion. Now, where are we with the development? In 2022, we built a lab prototype and did a lot of lab testing at the Rijswijk Center for Sustainable Geoenergy of TNO. This is how we know how to do good hole cleaning and how to keep circulating pressures safe. We also have done numerous drill tests under downhole hydraulic conditions, and that's very important. Steel shot erosion makes the drilling faster and more energy efficient, and for the specialist, the combined action of the PDC cutters and the steel shot erosion reduces the specific energy for drilling quite a lot. And last June, we had the first pilot of the DSSD field prototype. The test was done in a 9-meter wide tunnel at Versuchsstollen Hagerbach in Switzerland. There we mounted the DSSD system onto a horizontal drilling machine and drilled 2 horizontals. And first of all, we of course learned a lot. And furthermore, what we also found was that switching on the steel shot injection, that way we could increase the drill rate by up to a factor 3, which is in agreement with the statement on the low specific energy. We drilled a straight section and made 3 turns in the range of 5 to 10 degrees per 30 meters, which agrees with the stiffness of the bottom hole assembly. Hole cleaning was good. Pump pressures were up to 200 bar, 3000 psi, kind of an industry norm. So we are ready to build the first DSSD unit for deep drilling. A deep pilot is already scheduled in the Netherlands in 2024, next year. So to summarize, DSSD is effectively an agile rotary steerable system that also drills fast while steering. And DSSD is great for fast drilling of long multilateral structures at any depth through any rock. And that's the connection, of course, to geothermal, because why is it so important to have this technology available for geothermal? Of course, we have shallow, geothermal, deep and ultra deep, and for all 3, DSSD can have a big impact. For shallow, DSSD is to drill curved borehole heat exchangers that produce 3 to 4 times more the heating and cooling per BHE than conventional vertical borehole heat exchangers can do. Then a shallow geothermal is also an existing market. A lot of drilling is done and there are many short lead projects, and that's ideal for field hardening. And we expect to be able to commercially drill a few of these already in 2024. For deep geothermal, a TNO study showed that the long multilaterals drillable by directional steel shot drilling can produce 3 times more heat per duplet well. And finally, DSSD for ultra deep needs tremendously large closed loop networks at depth. And since DSSD drills very fast while steering, it seems to be ideal for drilling these structures. But we do need to add cooling while drilling for the downhole electronics. Now, Canopus owns the DSSD technology, but many organizations joined us in testing and demonstrating DSSD. I'm very happy to acknowledge the cooperation with all these great partners. After all, only together we can wake the energy giant. Thank you very much.
All right, so that was Jan Jette Blangé. Now we can see you, Jan Jette. Thanks a lot for your presentation about the steel shot technology that can actually reduce significantly the cost of drilling. I'm going to ask now our friends, our judges, who wants to start with the questions. Please go ahead, Michael.
I hope you can hear me. I appreciated the presentation. Thank you. My name is Michael Weber, and I saw your list of partners were very impressive, including Engie, where I used to work. So it was great to see. Could you describe the different partners and what their role is? Are they research partners? Are they development partners or offtake partners for the power? What is their role, the different partners you listed?
Yeah, thank you for the question, and good evening, Houston. These partners are a representation of the various stakeholders for geothermal. So there are about 3 or 4 different end customers, say energy companies in the consortium. There are also 3 institutes, TNO, the University of Zurich, and also the University of Calgary, involved and bring in their expertise to provide also that side of the portfolio, of the scope. And then there are, of course, also operational companies experienced in the geothermal and also on directional drilling that provide also operational support. That is so important to combine that experience with a new technology in field conditions.
Thank you.
Salvador. Yeah.
I cannot hear the question.
Hi, thank you for the presentation. I wanted to ask you if you have run any economic projections. We didn't get to see those during the presentation, so we're just wondering if you had done any of that work.
Yeah, of course. So there are also investors that put a lot of money into Canopus. And of course, they want to have also the long-term view, and for us, it is important as well. It is therefore also important to stress that we are targeting not only a deep and ultra-deep geothermal, which are still pretty uncertain markets, which can go many directions and are dependent on these breakthrough technologies, I believe, to make them really big. But we have also the shallow drilling market, which is already an existing market, and hundreds of thousands of shallow wells are already being drilled, which is a great, like I mentioned in the video, which is a great way to de-risk and field harden the technology and really make a contribution to all these different aspects of geothermal. If you look at numbers, then there is a similar effort required to get, or even bigger, to get geothermal to the scale of energy production of oil and gas. And if you look at the directional drilling and bit market, then you talk about an over 10 billion market for only the drilling, the hole making technology itself. But it's similar like the big breakthroughs that we have had over the last 50 years for PDC drilling and the rotary steerable drilling. These technologies opened up quite a big, a wider spectrum of wells and well designs that also boosted the oil and gas market quite a lot. And with this capability, it's not only higher rate of penetration, but it is also this agile directional control and being able to kick off out of an open hole, which enables a much more advanced, say, structures in the reservoir that you want to produce from, structures that are similar to the tree root structures or blood vein vessel networks, which have a much lower drawdown and have a much higher efficiency in their production.
I have a two-part question, if you don't mind. The first is related to the technology itself. You have IP protection around it and the linkage between what you're offering and what I believe NOV or some other companies have also developed something similar. The second part of the question is related to additional testing that was done to ensure the longevity of the bottom hole assembly, considering, you know, adding particles with electronics, and is this going to be a long-term solution that is actually reliable to drill these multilateral wells?
I'm sorry, I missed the first part of your second
was
question.
Around intellectual property protection of IP, and how this compares to other potential similar technologies, I believe similar technologies that maybe NOV or some others have.
Yeah, so what I know of course, this is not about the technology of the others, but what I know of the NOV say technology development is that it aims at rate of penetration increase, and our system is also a rotary steerable type of technology. And apart from that, the IP filings was no problem at all, so it was not interfering with existing patents of others. It is really a different approach. What I believe is critical is that if you combine these two hole making technologies, that you combine in such a way that you have them act together. Otherwise, you would have one of the two mechanisms for hole making dominating the rate of penetration. And I believe that we have a great synergy between the steel shot erosion and the PDC cutting. The second part of your question, you broke up a little bit here.
It's the longevity or the kind of reliability of the BHA, considering you're adding particles with potential electronics, if specifically for the multilateral wells.
Yeah, so if you look at the complexity of the steering sub, it's very similar to a directional module, an MWD device in combination with a pulsar. It is not more difficult than that, and there are no pads being pushed out and mechanical forces. It's really the timing of the particles and the manipulation with hydraulics of the particles that makes the technology very robust. And it can be maintained, for instance, on the rig side easily. If you look at the bit itself, then because we we limit ourselves to pressures that are below 5,000 psi or 350 bar. That means that we have not seen wear on during the pilot of the bit itself because of the steel shot impact. What we did see is that we should make sure that the distribution of the load, because of the interaction with the steel shot over the cutters, is balanced, and we had good results, but we can improve even better on that. Longevity, I expect, if you look at the battery use, for instance, very important for downhole use. We can easily, with one battery module, we can operate the steering sub for more than 4 days. So say 100 hours at least, which makes it, of course, very great to drill one whole section in one run, especially at a higher rate of penetration.
Thank you.
Quickly, yeah. So wondering if there's some loss of effectiveness as you go up in temperature, as the metal softens. Do you get less of the abrasion and impact effect? So what's the maximum temperature you've tested? And two, how do you propose to deal with hydrothermal, reservoirs where you're looking at air drilling and you don't have mud to convey the particles?
Yeah, I think if you look at the maximum temperature, because we have electronics in the device, that is the limiting factor for the electronics. So that's the battery packs. I believe the best ones are up to 200 degrees centigrade. And also the electronics, you have to be not exceed at least the temperature of those electronics beyond 180 degrees or something. So you need additional cooling of the system and insulated drill pipe, for instance, to keep the electronics going. The bit itself and the steel shot, they have much higher temperature rating than the electronics. So that's definitely not a limiting factor. During the impact, the temperature increases anyhow, and you can use the steel shot up to 700 bar or even a kilobar pressure drop over the nozzle, which we are not going to do. And during that impact, the temperature goes much higher, and the steel shot even survives those type of impacts.
Fantastic. Thank you very much, Jan Jette. We're moving on into the next pitch. That's coming from Ireland, and please.
Thank you.
Hello, everyone. My name is Simon Todd. I'm the CEO of Causeway Energies. Founded on the island of Ireland, we have an expert core team and a great network of partners, both in industry and research. Our mission is to decarbonize industrial and other large demand heat. Heat is a decarbonization challenge measured in terawatts of energy and gigatons of CO2 equivalent emissions. Heat accounts for around half of the energy emissions in the world. It's also a $1 trillion market that is ripe for disruption. That's because decarbonization is not just about climate mitigation. It's also now about energy security and energy affordability. We use geothermal resources as a supply and a store of thermal energy. We use industrial heat pumps as the engine to move heat and elevate the temperature to required levels. We call this enhanced direct use. We have a pipeline of 12 projects in early stages of development. The competitive economics and carbon savings of our projects depend on a balance of capital costs of the geothermal boreholes and the electricity costs associated with driving the system in operation. Most of our current projects involve heat up to 80 degrees C. If we could do more than 120 degrees C with the same cost competitiveness, our total addressable market doubles. So we've been looking into high temperature geothermal heat pumps. We found that we could use conventional industrial heat pumps to deliver 120 degrees C or more. But our low temperature, shallow geothermal heat needs 2 or more cycles to raise it to the required temperature. That causes our efficiency or coefficient of performance to drop below 2. And that hits our economics hard because of higher operating costs associated with higher electricity consumption. We also could drill to 2 kilometers depth and harvest 50 degrees C heat to get the COP back up to 3 or better. But because unit drilling costs go up at least an order of magnitude below 1 kilometer, it's now drilling capital costs that cripple our economics. So what if we could use low-grade heat from less than a kilometer depth with a heat pump system that lifts the temperature to more than 120 degrees C and still has a COP of 3 or better? Cheap geothermal heat and low electricity consumption combine our radical breakthrough in overall cost competitiveness. Well, our patent pending system and method does exactly that. It's a heat pump that maximizes the efficiency of a supercritical CO2 cycle with 2 novel additional components. And it's fed by closed-loop boreholes with a new design that maximizes energy recovery. In partnership with the Southwest Research Institute in Texas, we have the system proven to TRL4. The next step is to build an at-scale prototype of the system, including the closed-loop boreholes. To do this, we need 2 things. 1, we need a new strategic partner like a heat pump manufacturer. And 2, we need around $6 million to build the system. Success doubles the total addressable market of enhanced direct use. It makes geothermal a big player in the energy transition of key sectors like pharmaceuticals and agriculture, food and beverage. Our success also accelerates geothermal in general. Through exponential growth of our projects, we steepen the learning curve for drilling geothermal boreholes, shallow and deep. We'll improve and calibrate subsurface modeling and prediction. We'll optimize closed-loop completions. And we'll develop a heat pump technology that can use any low-grade heat, not just shallow geothermal. Causeway's mission is to decarbonize heat. Our beginnings are focused and modest, but our goals for geothermal are ambitious and global. We hope you will give us your support. Thank you for listening.
Right, so we have Simon on the screen. That was a nice presentation about how to crack the code for industrial heat and geothermal. Passing the word to our judges. Who wants to take the first?
How does your levelized cost of energy compare, I mean, to standard systems?
Yeah, nice to be here.
Thanks for having me. To answer the question, the levelized cost, as I explained in the video, depends on three factors. One is the capital costs of the heat pump and the borehole heat exchange. The second is the COP of the heat pump system, which acts as like a fulcrum to a balancing act with the third factor, which is electricity costs. And so the projects that we've been working on thus far look as if the levelized cost of heat is less than 10 cents per kilowatt hour thermal, which puts it into the same ballpark as natural gas boiler heat. And that's not without pricing that's not with pricing the carbon savings, which is another matter to be addressed.
Michael, I think you want to.
Yeah, I've got a question. Thank you for your presentation. Can you explain either your level of technical maturity? Is this at early stage? Is this already in the field? Is this ready to ship to customer? Like, where are you in product development maturity?
Yeah, so for this technology development, it's technology readiness level 4. So it's based on computer modeling only at this stage. So the next step is to build finish the design and build a prototype of the system that will take it at least to 5, if not to 6. And then after that is the first pilot with a committed client or customer.
Question on your approach on how are you going to
No, I can't hear.
Can you hear me now? Just a question on how you're going to monetize the value of this. Is the intent to be a service company that sells and service, leases, or to sell the product? Considering what you commented on, you're partnering up with a manufacturing company. And I guess the second part is how much of that differentiation will remain with your company versus the actual manufacturers?
Right, really nice question. Thank you, because it gives me the opportunity to explain that Causeway Energies is about being a developer. We want to develop projects and even better still, find finance for the upfront capital costs for the customer, and therefore give them an innovative combination of both a clean energy solution, but one that is affordable and predictable in terms of financing. So for the technology, we have no business or no wish to be a heat pump manufacturer. And therefore, with time, the partner that we're looking for, both for the the closed loop borehole completion and for the heat pump itself, we're very keen to find a partner that will actually, be much better placed to be a manufacturer, an OEM of that system. Not just the heat pump itself, but the package. So our strategy on IP is to bring IP to market that we think is going to help, and make sure that we're at the front of the queue in using that IP.
Thank you. Salvador?
Can you comment on how your technology differentiates from competitors? What is unique? What is different from similar competitive products?
So as I explained in the video, in principle, you could use current off-the-shelf industrial heat pumps that have temperature lifts of 60 or 70 degrees Celsius, or more correctly, Kelvin. And in order to use those for higher temperature heat, like 120, 150 degrees Celsius, you'd need to drill in average geothermal conditions, which is what most of the world is used to. You have to drill to 2 or 3 kilometers to get that source heat. So we could do it that way, and using conventional off-the-shelf geothermal industrial heat pumps. But this idea and this concept and this IP is unique, because what we're saying is, instead of using higher grade heat for the source, we're using lower grade heat, 25 degrees C, and therefore we do not need to drill to that depth. In fact, we only need to drill to less than a kilometer depth, 800 meters in average geothermal gradient situations. And in other words, the heat pump is doing the work in upgrading the heat. But the fabulous part of our heat pump design is, it's still, although it's lifting the heat, 120 degrees Kelvin lift, it still has a COP of 3 or better. In other words, for every 3 megawatts thermal of heat, you're only using 1 megawatt thermal electrical of electricity.
Excellent. Thank you very much. Let's give an applause to Simon.
Hi, everyone. I'm Andrew Lee, president and co-founder of Innovia Geo. And it's such an incredible honor for us to present to you today. I want to start with a simple question. With everything we humans have created, doesn't it surprise you that we still heat the vast majority of our buildings and homes with this? It's the same basic process we used when we lived in caves thousands of years ago. Hi, everyone. I'm Andrew Lee, president and co-founder of Innovia Geo. And it's such an incredible honor for us to present to you today. I want to start with a simple question. With everything we humans have created, doesn't it surprise you that we still heat the vast majority of our buildings and homes with this? It's the same basic process we used when we lived in caves thousands of years ago. So why is this a problem now? Because now there's over 8 billion of us on Earth, and it turns out heating and cooling is our single largest energy use. And most of this energy comes from directly burning fossil fuels for heating and increasingly power-hungry air conditioners. But this also means there's a huge opportunity, a $500 billion opportunity, actually. Luckily, there's a decades-old solution that can help us, and that's geothermal heat pumps. These systems work by simply moving heat between a building and the ground. And because the ground temperature is much more stable than the air, they're incredibly efficient and produce 0 direct emissions. So why aren't there geosystems everywhere? What's the catch? As some listening probably know, the catch is geosystems are costly to install because they require drilling hundreds of feet deep, multiple times for each building. So although geosystems are incredibly efficient, they have long payback periods, and that's really limited their adoption. Today, less than 0.1% of our buildings currently have geosystems, and only about 10% of buildings are economically viable with conventional technologies. And don't get me wrong, conventional geo heat pump systems work amazing. And there are incentives and incredible companies out there doing great things to get that 0.1% up to 10%. And we need that to happen. But we also desperately need to enable geo for those other 90% of buildings. And that's what we're focused on. Expanding the geo market with technologies that can cut the cost of a geosystem in half, specifically for low and mid-rise buildings and homes. And how we're doing that started with one simple question. Do we really need to drill so deep? And the surprising answer is we don't. And that's the key to the new approach we've taken at Innovia Geo, to develop shallow geothermal technologies that can operate as little as 50 feet deep. That's the length of a standard transport truck. And with this one change in approach, it allows us to do something incredible. We can bring an entire industry that drills more holes in the ground than any other into the geothermal tent with us. And that industry is the foundation construction industry. At these shallow depths, we can integrate our geothermal systems directly into building foundations, avoiding the need to drill. Where we can't do that, we can use foundation construction techniques to install our systems at speeds 3 to 5 times faster than conventional rotary drilling. And most importantly, we can bring the resources and talent of our foundation industry colleagues to bear so we can quickly scale. And this isn't just theoretical. We're getting real world results that our shallow systems work at our full-scale pilot system that's been heating and cooling this building in the city of Waterloo, Ontario, Canada for the past year. And it's an incredibly exciting time for us because we're just getting started on our first commercial pilots with the goal of being able to offer turnkey systems on a design, build, operate basis within 2 years. And if we seize this opportunity and accomplish our goals, after thousands of years, change can finally happen. Geothermal is the missing piece to a sustainable future. One where we get all of our energy, power, heating, and cooling from our natural resources, the wind, the water, the sun, and of course, the earth. Thank you so much for the opportunity to present today. We would love to connect with anyone listening that would like to learn more and help us on our journey.
The foundation construction industry into geothermal. Who wants to go first?
Yeah, hello. About the timeline. In your timeline, you show your MVP pilot as completed, and I would like to know more about it. You know, when did it take place? How was that the pilot conducted?
Sure. So the pilot structure, the building, is a substation service building. So it's installed with one of the local utilities in the city of Waterloo in Canada. And the facility was commissioned about 2 years ago. So we completed about 2 years of testing with the system operating almost completely on its own for the past year. And the system has a conventional deep vertical traditional geothermal system installed as well. So we've been able to do side-by-side comparative testing between our shallow system and the deep system that's conventional.
I have a question on, I couldn't really understand the technical differentiation, understand kind of the outcome that you could install this at a shallower depth,
Sure.
be able to make it easier, but it wasn't clear what you're offering.
Sure. So we developed a way to extract and exchange that heat with the shallow ground. And what the common misconception is that we need to drill deep for that resource. But that temperature is the same whether you're at 30 feet or a couple hundred feet down. Only when you're a kilometer deep is really when that temperature starts to increase and you get that heat from the earth. So we've designed a ground heat exchange system that can efficiently exchange that heat at that shallow depth, at that depth of 50 to 100 feet deep, specifically so that the foundation construction industry can install those systems. The other characteristic that the system has is an inherent thermal storage or recovery property, and we can utilize that property in a controlled manner so that we can actually improve the efficiency of a geothermal heating and cooling system by about 25%.
So I like that you're attacking a giant section of the market, the thermal needs, but it again is still not entirely clear to me. How do you extract value from that market segment? Is it through a license, a sale of this heat exchanger design, or are you going to actually develop the projects yourself and then sell the energy to the buildings?
Sure. So the first step in our plan is to develop a full capability so that we can offer a design, build, operate offering to the market. And the two customer segments we're focused on are those developers and building owners themselves, but also utilities. And so there's more utility companies out there that are building and owning geothermal systems as a third party on a utility basis with building owners and developers. And so we want to tap into that segment to be able to, grow and expand and scale with. And then at a certain point in time, whether that's scaling or not, we can also choose to become a geothermal utility ourselves and finance those systems for those homeowners and building owners.
I have one more question since we're saved one here. But the economics are also not very clear. How much is the capital investment, potential operating cost difference from the current model? And, there's many mature areas, kind of Norway, considering kind of how they do the heating system there. How would this, is there a side-by-side comparison to see if this model would be scalable?
Yeah, so in a conventional geothermal heating and cooling system for building or home, the typical payback can be in excess of 10 years. And so with these foundation construction methodologies, plus the operational efficiency savings from operating those systems about 25% more efficient, our goal is to cut that payback in half so that we can get it under that 10-year time frame into a frame where that can be a decision point for building owners and developers to take that on, or as a third-party utility, you can finance that with, for example, a 20-year energy service contract.
Thank you.
Excellent. Thank you very much, Andrew, for your presentation.
Thank you, everyone.
Moving on, next one is Cindy Taff from Sage Geosystems.
So this is where it all began over 2 years ago. I'm Cindy Taff, CEO of Sage Geosystems. Our team has over 150 years of combined oil and gas experience, over 200 patents, and more importantly, we have a track record of turning technology into reality in the field and deploying it globally. So at Sage, we have developed cost-effective energy storage solutions deep in the earth, as well as geothermal solutions for hot, dry rock. This is our test well. We're in Starr County, Texas. This well was drilled in 2008. It's got 9 5/8" casing down to 11,500 feet, and it's got a bottom hole temperature of 300 degrees F or 150 degrees C. So in 2021, we re-entered the well and we created a 3,200 foot vertical reservoir in hot, dry rock using our gravity fracturing technology called heat root, which allows you to frac downward toward the heat. After creating this artificial reservoir, we spent the next 4 months testing the most effective way to operate that artificial reservoir to get the most net power out of that geothermal system. So what we have developed is a cyclic EGS technology that we think has cracked the code plaguing the EGS industry for over 40 years. Some of the challenges being from the EGS technology is having to connect fractures in the subsurface between wells, the huge parasitic load from pumping water from one well to another as you go in through that fracture, which means that your net output or power output is going to be lower. And then the tendency for that water to short circuit or find the path of least resistance, meaning that the surface area that you have to harvest heat from the earth is going to be smaller, and your net output is going to also be smaller, and you're going to have cooling effects. The most important thing that we have learned with this cyclic EGS technology is that we can harvest both the pressure and the heat energy of the water coming out of that artificial reservoir, which means that our net power output is going to be significantly higher than other EGS technologies, and our cost is going to be lower. So in a nutshell, our EGS technology is going to deliver a cost-effective commercial geothermal system for hot, dry rock in formation temperatures greater than 300 degrees F or 150 degrees C. Now, during this testing, we also discovered that we have the perfect energy storage solution. So just a few months ago, back in February of 2023, we came back to this well and we demonstrated energy storage for over 5 weeks. So during this testing, we were able to demonstrate long duration energy storage. So we pumped into the well or stored for 6 hours, and then we produced 200 kilowatts of power for over 18 hours. Now, if you can imagine, if you combine that with solar, you can actually turn solar into 24/7 baseload energy. Also during the testing, we were able to demonstrate load following energy storage, meaning that we released all of the water from that fracture within an hour, and we were able to generate 1 megawatts for 30 minutes, only limited by the size of piping that we had on the surface, which was rental oil and gas equipment. So our modeling and our field results has shown that we can compete cost-wise, both upfront capital and levelized cost of storage with pumped hydro storage and lithium-ion batteries, and we can compete now. So we are moving very quickly to our first demonstration power plant in mid-2024, where we're going to be doing our mechanical energy storage, which does not rely on bottom hole temperature, which means that you are not geographically limited. So I want to thank PIVOT2023 for this honor of being nominated for Startup of the Year. Congratulations to all of the other companies that have also been nominated. We're really looking forward to the outcome of this award. Thank you.
Right, so that was Taff and Sage Geosystems making storage the buzzword of geothermal. Who wants to start?
I've got a great presentation, 2 questions. One is for storage, can you give a sense of scale in megawatts or megawatt hours or gigawatts, gigawatt hours, or a sense of scale? Second question, you mentioned the IP portfolio of like 200 or more patents. Can you explain whether those are your patents you developed or you have licensed the technology or IP from other places? Thank you.
Yep, great questions. Thank you. Our megawatt per well for energy storage is 3 megawatt net. That's net of all the parasitic loads. And sorry for the confusion. The team, when we were in the oil and gas industry, had over 200 patents. The patents that we've accumulated now in energy storage and geothermal is about 20.
Okay, thank you.
Who wants to go next?
Great presentation. Thank you for that. I wanted to ask you about when you're fracturing the well, you're showing the fracture grows downwards, right? And my question is, how do you ensure you're not going to have that frac, the height of that frac being created growing upwards?
Yeah, so what we're doing is a method called gravity fracking. If you think about when drillers are drilling and they lose circulation, we're doing the same thing. So we're fracking with a heavy fluid, meaning that the fluid weight is greater than the fracture gradient. So we don't have to pump at high pressures or high rates. We're letting the fracturing fluid do all the work. And so the tendency for the fracture growth will be out and downward as compared to the oil and gas industry, which typically will use water, and they're pumping at much higher rates and pressures, which means that the growth would tend to be out and up. So we're using, again, a heavy fluid that will be heavier than the frac gradient, will then tend to go out and downward in that frac growth. And this is just to mention real quick, this is a technology that's been used actually dating back to the 1960s, where the nuclear industry used it to actually dispose of nuclear waste.
So you talk about a bunch of technical advantages, and by the way, I'm going to ask you some questions over beer tonight because I like this. You talk about your technical advantages versus traditional EGS, but so how do the economics compare? Translate that to me into an economic advantage versus traditional EGS.
Yeah, no, that's great questions. You know, we have an oil and gas background, and so we are always focusing on the economics because we know technology can be fun and sexy, but if you can't make it commercial, then you're not going anywhere. So let's talk about geothermal, not energy storage. So geothermal, a first of a kind, we can install for $9 million per megawatt, which equates to a levelized cost of energy of about 9 cents a kilowatt hour. That means we're not real, competitive in Texas, but we go to California and Germany, and we can get people very excited. But as we scale up on a multi-well pad, we use, supply chain synergies, and we're just in a scaled up mode. So say 50 megawatts, then we can drive those costs down to more like 4 to 5 cents per kilowatt hour LCOE.
Thank you.
I have maybe a follow-up question to that. You had a wide range of temperature kind of application. At what temperature range are you assuming that economical assessment or economic assessment, is this within a feasible range of where the current well profile technical ability is?
Yeah, let me be clear too. For EGS, not for the energy storage, what we're targeting, because energy storage, we don't need heat. But for the geothermal EGS, we're targeting between 150 and 250 degrees Celsius. And the reason why we're targeting that is, first, we think that's going to be enough heat so that we can make geothermal economic. But we can also use existing oil and gas equipment, and we can use it now to start scaling geothermal. So I would say a sweet spot for us is about 200 degrees C. But I will comment that we've been doing some modeling. Our team has been doing some modeling in a very hot ambient temperature area, the Middle East. And so because we all know geothermal is about delta temperature. And so for that area, we're actually wanting to get to a little bit deeper, hotter, so maybe 220 C. But typically we're looking at between 150 and 200 C with a normal ambient temperature.
A second question was more on the technical side. The longevity of kind of the solution, you're depending a lot on Mother Nature, the breakthrough of the fluid within that fracture, and also maybe question on any subsurface testing that you've done to really validate, is the fracture going to the bottom? And do you have really longer term testing to show that the flow will continue to actually have a larger exchange with the reservoir versus a short cycle across?
So in the field, we've done about 6 months of testing, cycling of that fracture. One thing to explain is when we create the fracture, we fill that fracture with a certain volume of fluid, and then what we're doing is cycling about 10% of that volume. And so the fracture tip never goes into tension, and so fatigue of that fracture is really not a concern. And because we're doing what we call zero voidage, we're putting into the fracture, we're taking a small volume out, and then we're replacing it. So we feel like over time, and again, we have about 5 or 6 months of testing, but we don't have 30 years. But we feel over time that the fracture is going to be very resilient. We do imagine that there's going to be some spalling of the rock off the fracture face, which means that when the fracture face closes, it won't exactly line together. And so that actually will create a more efficient system for us. And so we think longevity is similar to what the oil and gas industry, designs their wells for, so 25 to 35 years. And we see no reason for the power plant longevity to be any shorter than that, because of course we'll be doing plant maintenance and change outs as needed.
Thank you.
All right, we're moving on. Thank you very much, Cindy, for your presentation.
Thank you.
Hello, everyone. Greetings from Norway. I hope you're all enjoying yourself, the PIVOT 2023, and hearing about all the technology developments in the geothermal industry. We are Tegwell. We're developing geothermal technology that we believe have the potential to push geothermal energy into the hands of everyone. Our team, Sondre Slatia, Benjamin Smith, Gunstein Skolmedal, and myself, Tomas Finnøy, have a combined experience of geothermal energy, energy materials, battery technology, computer science and engineering, and automation. And we are working with Indian universities of Bergen, Reykjavik, and Agder. So our goal is to be able to give access to geothermal energy to anywhere in the world. And to do that, we have to solve the issue with the dependency on specific geological conditions. And we need to have electrical power production, which can be maintained by everyone. So we decided to go for a closed loop system that is reliable, it can last for a very long time, and doesn't need any maintenance from specialists or drilling companies. The well needs to be enhanced, however, because a closed loop system does not produce a meaningful amount of energy without it. So we've developed a method to increase the conductive properties of the rock surrounding the well by injecting conductive material into it. And we do that by using a method called radial jet drilling that drills canals from the wellbore, which we then again fill with highly conductive material. This method has the potential to increase the well's output several times. Instead of using a complex device like a turbine to produce electricity for a local community, we just decided to design our own power plant based on thermoelectric generators. A thermoelectric generator is made up of completely non-moving parts and produces a little bit of electricity from the energy provided. It is completely silent, it's maintenance-free, and our design is very easily transported, installed, and upgraded once new technology is available. So the combination of our enhanced well with our thermoelectric power plant is the perfect candidate for supplying green geothermal energy to remote locations where the electric grid is not either stable or accessible at all. Maybe the best place to put it would be in a politically unstable region where energy is something people fight over. This can be easily protected and easily maintained by a local community anywhere. How about remote industries that have need for clean energy? The ideas come flowing once you start thinking about the possibilities. Maybe you are already. I know we are. Okay, that was it. Thank you for listening. Thank you for the judges for making us a finalist. I hope everyone finds this interesting, and I hope our competitors have as good time as me having this talk. Okay, thank you very much then. Bye-bye.
So that was Tomas from Tegwell, a company that is focused on enhancing the transmission of heat thanks to this new conductive material in a closed loop system, combined with thermoelectric generation at the surface in a way to enhance the opportunity to generate heat, power from heat. I pass the word to the judges and see if...
Thank you for your presentation. Can you tell us about your team? How big is your team, and how many people are working at the company on this technology?
Yeah, we were in pre-funding state right now. We are 4 people working on this project, but in collaboration with the 3 universities and 2 other companies, which I can't name right now. So in total, we're 4 people involved with the project, but outside in other companies, of course, there are other people involved, which I can't really number right now.
Apologize. The audio was very difficult to hear in the room here, so I'm going to ask two kind of quick questions, and maybe you covered it. But so, how far along are you in the actual demonstration of this technology? I don't know where you are in the development of it. Number one, and number two, I didn't quite hear how much the improvement was in the conductive heat transfer efficiency, right, by using this material versus simple AGS. I'm trying to get to how do your economics improve measurably with this technology?
Yeah, right. We are in the simulation and design phase for the downhole technology. We're also in talks with a drilling partner, which are developing technology to perform this this method. The economics behind it, the potential, what we're simulating right now using existing materials, conductive materials, we have models which give us up to 1.5 to 2 times the amount of energy out from a well at any depth. There's no limitation to how deep we can go or what temperature we can drill at, according to our partners and our simulations. We are taking advantage of being able to modify the entire wellbore length and following the geothermal gradient along the way. So the deeper you go, the more energy you get out, obviously, but limited by the normal drilling costs, of course.
Salvador, Rami, you want to come in?
I'll take it. Yeah, I mean, okay, great. So you're 1.5 to 2 times the energy content. Have you, from a total economic standpoint versus the cost of your material and your treatment to extract that additional heat, how do you think that you're going to compare versus traditional AGS?
Well, the LCOEs we've been calculating is looking extremely good compared to other green energies. Of course, our major benefit is that our wells will be incredibly stable after they've been prepared. They won't be, you don't stop producing energy from it after 30 years, but they can last for 50 or even 100 years, of course, since they're completely closed loop. The energy material we pump into the well stabilizes it more. So the LCOEs we have been seeing from our calculations. Also, I just had to add that the material, the conductive material that we pump into the wells can be improved many times, being that it's not been much developed as yet. So that's an area we want to explore further. So the potential for the well is more than 2 times. Also, the number for LCOE, for example, for a well that produces about 250 degrees Celsius at 7 kilometers depth is up to like $50 per megawatt hours, for example. That's, of course, utilizing direct heat as well. The major benefit of thermoelectric power plants is, of course, that it's completely maintenance free, which lowers the cost over time as well. So yeah, thanks.
I have 2 questions. The first related to intellectual property. Do you have any unique intellectual property, and what differentiates you from? There's a lot of superconductive material out there. What's different about what you're providing?
We have patent pending on the actual method of preparing the well with using the radial jet drilling methods and filling it with conductive material. That's our patent so far. We have not so far as of yet patented any specific conductive materials, but we want to explore that area soon. Yes.
A second question is related to supply chain. Is there, I guess, either the material or whatever you're using, is there any limitations within the market on availability of it?
Not as we know. The material we're looking at is a composite with carbon and other metals, or I can't remember the name now. Carbon nanotubes and combined with metals, such like that. So it shouldn't be any limitation in that regards. But of course, the method to prepare the well and how to prepare the well is not yet 100% known to us. But there shouldn't be any limitations to the supply, but no.
All right, thank you.
Thank you very much, Tomas, for your presentation.
Okay, thank you.
We reached the end of our pitches. I'm going to take our judges to the decision room while you thank them for their time and their